Okay, good afternoon, students. In the previous class, we have studied about the reflection coefficient and little bit on the transmission lines equations. We have derived the equations. Just a recap of what we studied in the previous class. So we have studied about the reflection transmission coefficient and derivation and solution of the transmission line equations, and derivation of reflection and transmission coefficient we'll see. I think we have completed this, but one more time we can go through this before we go ahead with the. So these are the equations which we solved with respect to reflection coefficient. Once again, we'll go through the reflection coefficient equations. The reflection coefficient of a transmission line is nothing but like a reflection, how much a transmission line is reflecting. So actually, ideally my transmission line should not give any reflection. It should, because in a transmission line means what? It is a connection cable or a connection between transmitter and receiver, where it should connect 100%, it should communicate the data. But whereas if I have some kind of reflections in the transmission line, then I should know how much is the reflection that transmission line is having. So because the amount of reflection will give you the how much actually efficiently my transmission is happening in the transmission line. So therefore, the definition of the reflection coefficient is given by, it is the ratio of the reflected voltage at the load to the incident voltage. That is, the reflection coefficient is given by VR by VI. That is VR is nothing but your reflection voltage or reflected voltage, and incident voltage is VI. Now this is a constant dimensionless quantity, where VI is the incident voltage of the load at load. So that is given by V is equal to e to the power of minus you can say gamma z, and VR, this is VI, and the VR, that is reflected wave, is given by V e to the power of your gamma z. It is a vector quantity, basically a complex number, and its value depends on the characteristics impedance of the transmission line, that is Z0, and the load impedance. So when you see the reflection coefficient in terms of that is your characteristics impedance and the load impedance, then we have a formula like this, which is given by reflection coefficient is equal to ZL minus Z0 by ZL plus Z0. That means load impedance minus characteristics impedance by load impedance plus characteristics impedance. So everyone, please note down this formula. This is very important formula. Now we will derive this formula. Now we'll there may be a question in the exam. Explain what is a reflection coefficient of a transmission line, and derive an expression for reflection coefficient in terms of load impedance ZL and the characteristics impedance Z0. So this question may come. So this may be a question for approximately 12 marks, 10 marks, like that, because the definition and explanation about the reflection coefficient will give you some around 4 to 5 marks, 4 marks, and probably the expression or the derivation of expression may carry 8 marks. So simple expression, simple derivation, simple definition. So we'll go through the derivation part. Now consider a transmission line having a characteristics impedance Z0, and which is connected to a load impedance ZL. That means this is a transmission line. Here we are not discussing about the source part. We are actually towards the load, because load is involved. So we are actually at the load end of the transmission line. That source is here, but we are not considering the source. So therefore, when we consider a transmission line with a load, then definitely there is a characteristics impedance which is actually applicable to this. So therefore, when I consider a transmission line, we have a incident voltage that is given by VI, that is a which is actually from the source to load, this is going. And also we consider, because since we are discussing about the reflection coefficient, we also consider the reflected voltage also, because we in practical we have some kind of reflections happening in the transmission line, because there is no 100% transmission line which is like capable of transmitting 100% waves. So that means there is no ideal transmission line as such. So therefore, definitely we'll have some reflections happening. So therefore, we consider the VI and VR and load impedance, then of course the characteristics impedance. Then we consider the L, that is the length of the transmission line, as L. L is equal to Z, because we consider some portion of the transmission line which is 0 to Z, the distance. From the definition of the reflection coefficient, we can say that reflection coefficient is given by VR by VI, that is the reflected voltage by the incident voltage, as per the definition. So when we substitute the value of VR and VI, so when we substitute the value of VR and VI, so we get this V into e to the power of plus gamma Z by V into e to the power of minus gamma Z. So this is the reflected voltage and incident voltage. When we do that, so we know the load impedance, that is the load impedance ZL is connected to the transmission line at a distance of L is equal to Z from the starting point of the transmission line. Therefore, ZL is nothing but your VZ, that is voltage, by current, that is IZ. So we know this equation. So therefore, the voltage and current through the transmission line at a distance L is equal to Z is given by VZ, that is V of Z is equal to V plus e to the power of minus gamma Z plus V minus e to the power of gamma Z. This we have solved this using the equations earlier. So this is the value of Vz, and Iz also we have solved it, that is which is given by I plus e to the power of minus gamma Z plus I minus e to the power of gamma Z. So these two equations we already seen. The characteristics impedance of the transmission line is also we have seen, we have derived this earlier. Z0 is equal to V plus by I plus, which is nothing but, if I take it in terms of I plus, which is nothing but V plus by Z0, that is characteristics impedance. Therefore, Z0 is also given by one more formula, that is minus of I minus V minus by I minus. So therefore, I can take I minus as minus of V minus by Z0. So when we have these two equations equating like this, then I can write I of Z is equal to V plus by Z0 into e to the power of gamma Z minus V minus e to the power of gamma Z by Z0. So we can have this expression. Similarly, when we have in terms of this also, I can take some simplification. I can take some common factor, that is Z0 is common in this. So if I take that, the final equation will become Iz is equal to 1 by Z0 into the bracket V plus e to the power of minus gamma Z minus V minus e to the power of gamma Z. So this equation we get. Now when we divide equation 3, that is this is the equation 3. When we divide equation 3 with 5, so this one Iz, that means Vz by Iz if I take. So what happens, this term by this term. So similarly, so Vz by Iz if I take, then I'll get the same expressions can be substituted here exactly. Now I'll do some simplification here. ZL, a little bit rearranging the terms. We know that Vz by Iz can be written as the ZL, that is our first term, that is we have got it here, equation number 2 here. The same number I can just substitute Vz by Iz as ZL, which is equal to Z0, because it is on the 1 by Z0 here can come up on the numerator side, and then we have the same terms here in this equation. So what I do in this equation is I will divide throughout by V plus e to the power of minus gamma Z. So if I do it, then this term will become 1 plus this by this term. So it will, I am dividing throughout numerator and denominator. So I'll get a term like this here. So now we also know that the reflection coefficient is given by V minus e to the power of plus e to the power of gamma z by V plus e to the power of minus gamma z. So therefore, we have same term here. The whole term can be replaced by this gamma. So therefore, what I can do, I'll in the next slide I can show. I'll ZL is equal to, I will just replace this. ZL is equal to, I will replace Z0 as it is. So 1 plus your reflection coefficient by 1 minus reflection coefficient. So if I put this, then I'll rearrange the terms. ZL into numerator cross multiplication I get, and a little bit rearranging terms and taking common. So I'll get a formula like this, and finally I get reflection coefficient in terms of ZL and characteristics impedance and the load impedance like this. That means the reflection coefficient is nothing but the ZL minus Z0 by ZL plus Z0. ZL is your load impedance, Z0 is your characteristics impedance. So my reflection coefficient can be, I can calculate. Now sometimes in exam what they do, they will ask what is the, calculate the reflection coefficient. Given data is load impedance is some, they'll give some value, and characteristics impedance value they'll give. They will ask you to calculate the reflection coefficient. Two terms, very simple formula, apply and get that thing all calculated. Now in this there are certain conditions which are applied. Now what happens if ZL is equal to Z0? We already discussed this thing. When ZL is equal to Z0, that is when characteristics impedance is equal to the load impedance of the transmission line, then what happens? My transmission line is perfectly matched. When I have perfectly matched transmission line, that means ideally I will not have any reflections in the transmission line. So when there is no reflection available in the transmission line, means my reflection coefficient will also become 0. So therefore, when I have no reflections, my reflection coefficient will become 0. Therefore, ideally my transmission line is 100%. But this is only theoretically we can say that. But when it comes to practical this thing application, so this is really difficult to achieve 100% transmission line, perfectly matched transmission line. But at some times we may also require such applications in certain sensitive areas. So, but it is very, very difficult to achieve. It's not impossible, but it's difficult to achieve. If now another case is ZL is not equal to Z0, which is the general practical situation where you are ideally the characteristics impedance of the transmission line is generally not exactly equal to the load impedance. Then this I call it as a mismatched transmission line. So mismatched transmission line means there will be some reflection. There will be some reflection. When there is a reflection, the reflections will have the magnitude and direction. So therefore, we know the reflection coefficient is given by ZL minus Z0 by ZL plus Z0. So therefore, I also represent in terms of the magnitude, how much magnitude, and the direction of the reflections are occurring. So therefore, this is there. So in a mismatched transmission line, we have a reflections existing. In a perfectly matched transmission line, we have no reflections. So there is no reflection coefficient. Now sometimes what happens in the exam, to make it difficult, what they do, they will give you a question like, okay, a perfectly matched transmission line is having a characteristics impedance of something. That's all. He will give the value of only characteristics impedance or the load impedance, and he will say that it is perfectly matched transmission line. Then we know that for a perfectly matched transmission line, the load impedance or the characteristics impedance are same. So any one of the term which is given is same. So therefore, they may ask you to calculate the reflection coefficient. Then definitely you have to prove it as a 0, because if the value is 0, then you have to put in the formula and show it as a 0. So this kind of questions sometimes we can expect in the VTube question papers. So then don't get tensed that only Z0 is given, ZL is not given, but they have mentioned that it is a perfectly matched. So had it been not matched, then of course you will have to have different values of characteristics impedance and the load impedance. So therefore, the reflection coefficient is measured at load is also called as load reflection coefficient, and it is also denoted by your like reflection coefficient. This is it is denoted by this one. So now comes the transmission coefficient. Now, what is the transmission coefficient? Transmission coefficient is nothing but your how much you what kind of transmission, how much transmission you are making, how much transmission is happening in the transmission line. So that is how we have to calculate. Now, how will you calculate that thing? Now, the transmission coefficient of a transmission line is defined as the ratio of the transmitted voltage, to the incident voltage. There it was different. Now here it is different. Now there it was reflected voltage by incident voltage. Now here it is how much is the transmitted voltage to the incident voltage. Now that is the difference. So it is the ratio of the transmitted current to the incident current in terms of current. Now I can write tau is equal to Vt. Now there in the reflection coefficient we saw it was VR by Vi. Now here it is Vt by Vi. That means it is how much voltage it is transmitting to the next transmission line or to the load by the incident volt. So in terms of current, it is It by Ii. So that is incident current. Now we have a transmission line here, the load ZL we have. So there now here this is the reflected voltage is also there, incident voltage is also there. Now what is the voltage which is transmitted? So whatever is the load voltage which is there, so that itself is your transmitted voltage. That means what? Whatever the voltage which is existing in the load voltage, whatever in the loads, like say this is the load is an antenna. If you consider this as an antenna, if the load is an antenna, then whatever the load which the antenna is transmitting here, whatever load the antenna is having here, that itself is your transmitted load. That is your voltage, transmitted voltage. So therefore, that means Vt is equal to VL. Whatever is the load voltage is the transmitted voltage, because now from here you can connect it to antenna or you can connect it to another transmission line, like that. So whatever voltage which is being in the load is the transmitted voltage. The same will go to the antenna and same will go to the your next transmission line. Therefore, we call Vt is equal to VL. That means whatever the load voltage which is there here is your transmitted voltage. But whereas here the VR is the reflected voltage, the voltage which is getting reflected. Now this is the incident voltage. The incident voltage means which is coming from the source to the transmitter side or the load side, transmitter to load side. The whatever voltage is coming is the Vi. This is your Vi, and this is your VR. VR is nothing but your reflected voltage. So this is your, but whereas VL is your load voltage and your transmitted voltage. So the transmitted voltage from load to next section of the transmission line is equal to the load voltage. That means Vt is equal to VL, I can write, and which is nothing but your Vi plus VR. So this is nothing but your Vi plus VR. That means the voltage which is coming from the source and the voltage it is getting reflected. Both if I add, then I'll get the load voltage. That is nothing but your transmitted voltage. So therefore, I can write transmitted transmission coefficient is written by Vt by Vi. Now this one. So we substitute the value of Vt in this. So when I substitute the value of Vt, that is Vi plus VR in this Vt, so I'll get Vi plus VR and divided by Vi. Already Vi is there. So if I just calculate the simplification, so I'll get 1 plus VR by Vi. So this is your this thing. So VR by Vi is nothing but your reflection coefficient, reflected voltage by incident voltage. So therefore I can write 1 plus reflection coefficient. That means what? The transmission coefficient is equal to 1 plus reflection coefficient. If I add 1 to the reflection coefficient, I'll get a transmission coefficient. So similarly, when I want to calculate the reflection coefficient, it is reflection coefficient is given by the transmission coefficient minus 1. So similarly, so both can be done. So they may give you in the exam, okay, reflection coefficient is something else. They may ask you to calculate the transmission coefficient, or they may give you transmission coefficient and ask you to calculate the reflection coefficient. So either way, so it is a very simple formula. We can just put it and calculate. So in terms of load impedance and the characteristics impedance, I can write transmission coefficient as like this. Since we know the transmission coefficient is given by 1 plus reflection coefficient, we also know the reflection coefficient value is ZL minus Z naught by ZL plus Z naught. Therefore, if I put it in the equation and do simplification, take LCM and other things and calculate this thing, then I'll get finally the equation like this, which is the transmission coefficient is given by 2 load impedance, 2 times the load impedance by load impedance plus the characteristics impedance. So please note down this. This is an important formula, very important formula. So please note down, and once if you're done with it, kindly let me know. These are very, very important equations. So many times the questions we have seen, these problems are coming. So once you know these things, so it is very easy to calculate the. So once any one item they have given, like if they give you the transmission coefficient, you can calculate the reflection coefficient. Or if they give you the reflection coefficient, they may ask you to calculate the transmission coefficient. So whatever may be the case, you should know the basic formulas. It will be easy to calculate. Okay, now coming to, there is something called standing wave ratio and VSWR. We will also deal with it very in detail, but basically with respect to transmission lines, we'll see some basic concepts of this. What is VSWR? Now, the VSWR is a voltage standing wave or the standing wave ratios. Now, what is this standing wave? There is something called standing wave in a transmission line. So we have seen incident wave or the reflected wave. We have seen all that transmitted wave and all. But what is this standing wave? Now, that means, see, when we talk about the transmission line, when we discuss about the transmission line, there are very important factors. That is, one is the incident wave is there. That is a wave which is coming from transmitter to load or the antenna. Then there is another wave which is going back from the load. It's getting reflected because of the transmission line is not 100% matched, because ideally it is difficult to achieve that 100%, but 95% or 99% we can achieve easily. 90% generally transmission line. So 10% of reflection there is always possible in the transmission line. So now what happens? Now this what do you mean by the standing wave? That is, standing wave is when we have an incident wave which is trying to go out like this. The wave which is trying to go out, and there is a wave. Some portion of the wave get radiated, and some portion of wave will come back. Like say around 90% of the wave is going out and 10% is coming back. Now, sometimes it may happen that 50% of the wave is getting radiated and 50% is coming back. That means my panda is 50% it is matched. So then what happens? There is a wave pattern existing. There is a transmitted wave and there is a reflected wave. Then there is a standing wave which is there in the like say example, if in the pipe, if in the water pipe, if I am trying to send the water out of the pipe, and I'll not allow the water to go out completely, but 50% I'll allow to go by keeping my finger on the my water pipe mouth. So what happens? Some water gets accumulated. And the water will not go easily outside. So the water will get stagnated in certain pipeline. So that is called as a standing water pattern. Now here, similarly, it happens for the electromagnetic waves. There is a standing wave. The wave will be stagnated at certain in the transmission line when it is not 100% matched. So that wave is called as a standing wave. Now we have to calculate what is the voltage standing wave ratio. We have to calculate that how much is the standing wave ratio is there. So that is very important. Ideally speaking, we should not have any standing waves in the transmission line, ideally, because whatever I am trying to transmit to the antenna wave, that should go out to the antenna. If it is not going, if the wave is coming back, then it is not desirable. So ideally I should not have standing wave, but because of the practical problems, we have some kind of standing wave always there in the transmission, and therefore we need to calculate what is the value of this standing wave, how much is the percentage, how much is the ratio. That is called as VSWR, that is voltage standing wave ratio, or ISWR, current standing wave ratio. Both are there. So what is that is the forward wave and reflected waves form a standing wave in a transmission line. So this is how it happens. So therefore, we have to be very careful in this when we are talking about the transmission line equations and transmission line we are dealing. So we need to understand the how much is the standing wave, because this is very important for an engineer when you are dealing with important practical aspects of the antenna microwave systems. So in a standing wave, there are positions at the line where the amplitude of the resultant the voltages has maximum and minimum, of course, because we have seen it is a sinusoidal wave, electromagnetic wave. So definitely we'll have different kind of patterns available in the electromagnetic waves. So what waves which are there? So how these are there? So now we have seen this is the voltage standing wave ratio, which if we consider now in this voltage standing wave ratio, this is the wave which we are having here. So we also know with our basics also, this is your V max, this is the voltage max, and this is your V minimum. This is V minimum and V max, and all these things we know all these things. So this is your peak to peak when you calculate and all. The distance between two successive maximum is equal to lambda by 2. Now this is one thing is there. Now between two peaks, peak to peak here, one peak to other peak, we can call this as a lambda by 2 in the standing wave ratio. So when we talk about this kind of situation, the VSWR is the ratio of the maximum voltage and the minimum voltage of the standing wave. That means I can define this voltage standing wave ratio in terms of V max and V minimum, so that I can write a formula like this. VSWR is given by a V that is modulus of V max and V minimum. So this is I can so this is the dimensionless. So therefore, and also we know VSWR can be written in terms of reflection coefficient, that is 1 plus reflection coefficient by 1 minus reflection coefficient. We are using modulus here. Now relation between VSWR and reflection coefficient. So we know this formula, that is VSWR is equal to V max by V minimum, which is nothing but VI plus VR by VI minus VR. That is incident voltage plus reflected voltage by incident voltage minus reflected voltage, which if I divide throughout by VI, then I'll get 1 plus VR by VI, 1 divided by 1 minus VR by VI, like this. So if we know that VR by VI is nothing but your reflection coefficient. So just it's a small derivation. So this I have derived VSWR in terms of your reflection coefficient, where your reflection coefficient is nothing but your voltage, that is reflected voltage by the incident voltage. So for a perfectly matched transmission line, we have this condition, that is your ZL, that is load impedance, is equal to the characteristics impedance. So and the reflection coefficient is also given by that is your 0, actually the value reflection coefficient, because ZL is equal to Z naught, so therefore it becomes 0. And VSWR is nothing, your 1 plus reflection coefficient by 1 minus reflection coefficient, which is generally it is 1. VSWR is 1 for a matched transmission line. That means if I have a transmission line which is a matched transmission line, perfectly matched, then I should have VSWR 1. If I have VSWR 1, I can say that it is a perfectly matched transmission line. Now, in sometimes what happens in exam, they will ask you to calculate the VSWR value, and they will tell that it is a matched transmission line. So ideally, you know that it is 1 because it is a matched transmission line. That means it has to be 1. So when you put the reflection coefficient value, whatever given data, see that you achieve 1 at least. That is 0.98, 0.99, like that. It is near to somewhere 1, 1.01, 1.02, like that. But it has to be somewhere near to 1. It cannot be more than beyond 1. So therefore, VSWR is equal to 1 circle is considered as the reference circle. Whenever we talk about the, we will deal with some kind of charts. They are called as Smith charts. So the Smith charts are used for calculating all these values. There is a reflection coefficient, transmission coefficient, and your VSWR. And all these things you can calculate using a chart known as a Smith chart. So that we will be dealing with that. So then in that there is a circle called as a VSWR circle. Now the VSWR circle, which is equal to 1, because it's always VSWR is equal to 1 for a perfectly matched transmission line. So we consider it as a reference point in the VS Smith chart. So that we'll see in the subsequent our classes. Now, to summarize all the whatever we have studied till now, before going to the voltage standing wave and standing wave patterns, so I would like to just use this technique to explain you the what are the final list of formulas. Please note down these formulas, very important, because this formulas once you are, it's a handy, and you will be able to understand and you will be able to interpret in exam and write in the exam. So the characteristics impedance of a transmission line is given by Z square root Z by Y, that is impedance by admittance. So therefore we know square root of impedance by admittance is nothing but your line impedance by line admittance, which is nothing but R plus J omega L by G plus J omega C, which we have already derived. And in that I can write omega is equal to 2 pi F, that is 2 pi frequency. Then next is the propagation constant we have derived. So this is characteristics, and propagation constant is given by square root of Z into Y. Again, the square root of your line impedance and line admittance. This is the propagation constant. And then we have the attenuation constant and phase constant. We have seen same thing when I represent in terms of alpha, beta, real and imaginary part. So this becomes attenuation constant and the propagation constant. Then we have reflection coefficient also. Reflection coefficient is nothing but it's in terms of load and characteristics impedance. I can write like this. For a perfectly matched transmission line, ZL is equal to Z naught, so this becomes 0. So for a mismatched transmission line, I have some kind of reflection existing, so which is in terms of magnitude and direction, which is represented like this. Then of course we have VSWR. VSWR, we have derived this. It is nothing but 1 plus your reflection coefficient by 1 minus reflection coefficient. So this is also another formula. So for that lossless transmission line, so for the lossless transmission line, we have pre-assumed things, because we know for a lossless transmission line, the resistance and the transconductance is always 0. So when we have resistance and transconductance 0, so therefore our characteristics impedance of a transmission line, when I substitute the values in this formula with 0 and R and 0, R and G is equal to 0, I can have a formula we have already derived, which is your square root by LC, L by C and all. We have already derived that. So just you note down this formula. Now let us solve some equations, some problems related to transmission line. Now please note down this formula, this problem, numerical. Numerical, a transmission line has the following parameters. R is equal to 2 omega mho, that is mho per meter, ohms per meter, and then we have G transconductance 0.5 meters second. This is actually mho seconds per meter. So equations are given in different, and frequency is equal to 1 gigahertz. L is equal to 8 nanohenries per meter. C is equal to 0.23 picofarads per. See, one thing you understand here whatever the values they are giving resistance, they are giving in 2 ohms per meter. That means the transmission line is of some length, which is a infinite length. Transmission line may be of infinite length. So we are talking about the resistance of the transmission line. I cannot tell what is the total resistance of the transmission line, but this is, they can say, per meter, 1 meter, every 1 meter of transmission line, I have 2 ohms of that is existing resistance here. That is how the transmission line parameters are explained. Similarly, the transconductance are also explained like this. And the inductance of the transmission line is 8 nanohenries per meter. Again, it is all with respect to per meter. The capacitance of the transmission line is also given by 0.23 picofarads per meter. So all transmission line has got all parameters, that is resistance, transconductance, line your inductance and capacitance, so which are actually per meter it is calculated. Now determine the characteristics impedance, propagation constant, attenuation constant, and phase constant. Please note down, everyone. So given data is R is equal to 2 ohms per meter, G is equal to 0.5 into 10 to the power of 3, F is equal to 1 into 10 to the power of 9 because it's in gigahertz. So L is equal to given by 8 into 10 to the power of 9 because the nanohenries. Then C is equal to 0.23 into 10 to the power of 2 minus 12 because of picofarads. So I have converted everything into a meter and terminologies. Then I had to calculate Z naught. I had to calculate your alpha plus J beta. I had to calculate alpha, what is beta, what is rho, everything I have to calculate. So therefore, first of all, what we'll do, we'll take a formula that is omega is equal to 2 pi f. 2 pi f. 2 pi f means what? 2 pi into 10 to the power of 9. That is 10 gigahertz that you calculate. So when you know this, omega is equal to 2 pi into 10 to the power of 9. So therefore, Z is equal to R plus J omega L. So therefore, this R is equal to 2. Now already know V2 value, and plus J into this value. You put omega L. Omega is the 2 into 10 to the power of 9 into 8. That is your omega L. L is your 8 into 10 to the power of 9. So therefore, what we get, if you simplify this, we'll get Z is equal to 2 plus 1 pi J, which is nothing but if you put it in the real and imaginary part, that magnitude and direction, in the polar form, if you write, then you get your 50.31 into this one direction, 87.72 degrees. So similarly, if I calculate for y is equal to j plus j omega c, if you substitute, you will get value that is 70 plus you will get this value is 1.52 into 10 to the power of minus 3 with direction 70.91 degrees. So these values I got z and y. So once I have z and y values, now I'll calculate the characteristics impedance, which is the first requirement, which is nothing but your z naught, that is square root of zl by zy. Everyone please note down this thing. Then I substitute these two values here, so I get a value here, and so therefore the final value will be 181.385 your 8.4 degrees. So this is approximately in the your polar and rectangular form. Real part and imaginary part, and this is the your polar form. This is the rectangular form. So then you have to write both in the exam. And then propagation constant. When we talk about the propagation constant, simple formula, square root by z into y. So you substitute the value. When you substitute the value, you get this value. Then you just do the calculation. So this is your polar form, and this is your rectangular form. Real and imaginary part. Then finally we have alpha is equal to, so we know this is a real and imaginary part. So with that, I can able to calculate directly whatever is the real part is your attenuation constant, and whatever your this thing is there, your phase constant. We have already discussed and we have seen this thing. So this is the problem. Please note down this thing. Important formula and important problem. Okay. So with it, we have completed this portion of the our transmission line system. Now we'll go to the other portion. We are still in a module 1 only. We would like to complete this module 1 before this weekend. So because otherwise we are lagging otherwise. So now coming to this module 1 part A only. Still we are in the. So we coming to standing wave ratio, that is VSWR, Smith chart, and single step matching. So we have in this last portion we have standing wave ratio, VSWR, Smith chart, and single step matching. So this is how the voltage standing wave happens actually when you are in when you are having a kind of wave which is there. So this is the transmitted wave, that is which is trying to go out. This yellow color wave which is trying to go out. and this is the reflected wave. Some reflections are happening back. So when we have a transmitted wave and reflection wave, then we have a some kind of stagnated wave in the, just like water in the pipeline. If you try to block the water from the one of the end, so it is just like same thing happening here. Voltage is get the voltages, the waves are getting stagnated in the transmission line. Transmission line is nothing like your just like your water pipe, and water is trying to go out, but that means the wave is trying to go out, but there are, because of the blockage, or you are trying to block the water, or you are trying to block the wave. So the, because there are some reflections happen, the wave is coming back in this pattern. So a transmitted wave with, along with the reflected wave, will form a pattern called as the standing wave pattern. This is the standing wave ratio, which has got some ratio to that. So and this is your Smith chart. Now this is the Smith chart which is required to, you are required to use this Smith chart for calculating various parameters, whatever we have discussed till now. That is the voltage standing wave ratio, your reflection coefficient, transmission coefficient, or any values you want to calculate, you can do it with this Smith chart. This is a simple Smith chart. I'll be explaining this all details of the Smith chart, how exactly this happens and all. So now we see, just to understand the standing wave pattern, because it's very important for an engineer, because if you are dealing with so many things in your future assignments, you'll be dealing with the transmission line, microwave antennas and all. So this becomes very important critical parameter in your when you're dealing. So this is your, see, there are so many waves are here. So this original wave is nothing but your actual wave which is trying to go out, that is blue color. This wave is trying to go out. This is the transmitted wave from the source, it's trying to go out. Now there is a reflected wave also, because see, most of the time what happens, most of the wave which whatever is transmitted by the source, because the transmission line is not 100% matched, 90% it is matched. So 90% of the wave is going out of the antenna, but whereas some 10% of the wave is getting reflected in the red form, which is shown in the red form. Now this is the reflected wave. When we have a reflected wave, then finally, because of the resultant of these two waves, that is blue and red, we'll have a resultant wave which is black, indicated in a black, which is nothing but a standing wave. This is the standing wave, is nothing but a resultant wave formed because of the original wave, or the original signal, and the reflected signal from the transmission line. So please understand this, very important. Ideally speaking, I should not have any standing waves existing in the transmission line. If you have more standing waves, then there are a lot of problems for you, and there are a lot of issues for you. But there are some applications where you require this kind of standing wave is required to achieve certain applications and uses. So those are also very critical. So it is as per your requirement of the transmission line parameters, you can design your transmission line and your sources accordingly. So wherever you want 100% my transmission should go to the antenna and get radiated, there you have minimum reflected energy, or you can have a almost perfectly transmitted matched transmission line. But wherever you desire that you should have a standing wave existing in your transmission line, then you probably have to little bit do a mismatch in a transmission line. Then definitely you're going to have the reflected energy, and you will have a standing wave in the transmission line. So what is voltage standing wave ratio? We have discussed about the standing wave, and we have discussed about what is how these are existing. Now we see what is voltage standing wave ratio. There is a ratio to the minimum voltage of the standing wave. So we have discussed that there is a wave, standing wave. I calculate the maximum voltage of the standing wave. I also calculate the minimum voltage of the standing wave. I take the ratio. The moment I take the ratio, it becomes your voltage standing wave ratio. That means maximum voltage of the standing wave to the minimum voltage of the standing wave will give you the voltage standing wave ratio. So this is very important. So now this is the generator, and this is the load, and this is the standing wave. So once you have a standing wave, the maximum is Vmax and V minimum is the V minimum. So this is there. This is not a normal signal where you are having only sinusoidal wave. We are talking about the standing wave pattern, which has got both. In this transmission, the standing wave, we have a transmitted signal also and the reflected signal. Both the signals are there. So therefore, it is a we call it as a standing wave. Now, distance between the consecutive maxima and minima is always lambda by 2. This is very important. Standing wave, that is superposition of incident of represented by Vmax is equal to V plus into e to the power of minus gamma t plus V minus e to the power of gamma t. The voltages, we know this, we have derived this. When you substitute in this formula, when you do that VSWRs also, 1 plus your reflection, 1 plus reflection coefficient by 1 minus reflection coefficient, and reflection coefficient being minimum is equal to 0. Therefore, when we have these conditions, we also have VSWR. Ideally, VSWR is equal to 1. If ZL is equal to Z0, then we have reflection coefficient is generally 0. Is ZL minus Z0 by ZL plus Z0 is equal to 0. We have already seen. And also we have VSWR, which is minimum I can have 1. Therefore, that means what? If you have any, whenever you are calculating VSWR and if it is less than 1, that means the value is not correct. So whatever calculations you have done, it is not correct. Now, the transmission line, VSWR is unity, and in Smith chart, there is something called a unit circle. Unit circle is called as a reference circle or a VSWR reference circle. So these things you should know. Then we deal with the Smith chart. Smith chart, see what is the timing now? So it's almost 25. So we are got with, I'll just cover the definition, and probably in the next class we'll see about the Smith chart, and we'll try to solve certain problems related to Smith charts. So now this is the Smith chart, very important one. Sometimes in exam they're asking you to solve certain problems based on the Smith chart. They will give a Smith chart, and they will you are authorized to use Smith chart along with your calculators. So when you use this, it is very easy to calculate. Because what happens is without Smith chart, it is very difficult to calculate all these parameters, the reflection coefficient, the transmission coefficients, and all. So using Smith chart, it is very easy to calculate such things. So Smith chart is a graphical tool used to find the transmission line coefficient, VSWR, single stub impedance matching, and techniques and all. We'll come to this single stub, what is single stub matching and all. But this is about the Smith chart basic properties. So we'll just see about definition. Smith chart, invented by Philip Smith in 1905, who stayed in 1997, along with Mijushai, is a graphical calculator or nomogram designed for electrical and electronics engineers specializing in radio frequency engineering. See, understand, these are the very important terminologies we are using here. So we are using here, I'll use the highlighter instead of pen with some color. So change the color also. So the Smith chart is invented by Philip, and see, these two people, they have invented it, and it is used for the radio frequency engineering to assist in solving problems with transmission lines and matching circuits. So this is very important. The transmission line and the matching circuits. The solving, you can solve the problems very easily related to radio frequency engineering, that is microwave engineering or RF engineering. The Smith chart can be used to simultaneously display multiple parameters, including the impedances, admittances. So we have impedances and we have admittances, and then we have reflection coefficients. See, all these parameters, that is scattering parameters or the noise circles, constant counters, regions, unconditional stability, including mechanical vibrations and everything we can calculate using this Smith chart. The Smith chart is most frequently used at or within the unit radius region. However, the remainder is still mathematically relevant, being used, for example, in oscillator design and stability analysis. So don't worry about all this. I'll just give an introduction. While the use of Smith chart, that is a paper, this is basically it is a paper with some circles with some kind of arrangements we have seen like this, basically concentric circles in this fashion. They are which are used for solving complex mathematical problems involving the matching problems has been largely replaced by software-based methods. The Smith charts display is still the preferred method of displaying how RF parameters behave at one or more frequencies as an alternative to tabular information. Thus, most RF circuit analysis software includes Smith chart option for display of results, and all but the simplest impedance measuring instruments can display measured results on a Smith chart very easily. So this is just indication of the Smith chart. You can just have a look of how the Smith chart looks. You can see the concentric circles. There are some concentric with respect to these circles. We have some scales on the horizontal scales are there with respect to the Smith charts. We'll see in the next class the whole how the Smith chart is operated. How can we calculate the various parameters on Smith chart and all. Okay, just I'll show you the some typical Smith chart calculations and all. In the next class, we'll see or deal with all the details of how this Smith chart is used for calculation of the. So then we'll see about the single stub matching in the next class. So with this, I have come to end of the session. So if you have any doubts in this, you can always discuss. No doubts. So I will take the attendance. I'll pick up the attendance. Then you can leave. In the meanwhile, I'll stop recording. Thank you so much for your patience.